And today's lecture is radiation hydrodynamics. In fact, you could probably give an entire week's-long lecture on radiation hydrodynamics. Perhaps actually Mark would have been happier if I'd done that. And so it's going to be rushed to fit everything in this one lecture, and I'm not going to be able to go into a whole lot of detail. On the other hand, radiation hydrodynamics really is an area where there's still a lot of research going on, and the methods are very much in development. So I'm not sure it's really time to give a overview or review. It's really an area of active research. So this maybe is discouraging and encouraging. Discouraging, I don't know, because you can't just copy somebody's code and implement it and it's going to be able to run everything with it right away. But encouraging because you should be looking for interesting problems that you can contribute to. Radiation hydrodynamics clearly, I think, is one of those where there's going to be a lot of progress the next 5 years. It's a very hot topic. Why is it taking so long? Because it's an extremely difficult topic. So I refer you to some classic books on the topic. Radiation Hydrodynamics by Mihalis and Mihalis and by John Castor. These are excellent starting points to learn about the subject. And numerical algorithms for MHD is really very easy compared to radiation hydrodynamics. And even though it took 5 years to develop very good methods for MHD, that's a piece of cake compared to radiation hydrodynamics. And why is it so difficult? Because, first of all, we don't even really have agreement about what are the right equations to be solving. Of course, you can write down the equations in principle, but solving them in a form that's, or writing them in a form that's amenable to a numerical solution is still a matter of research. Should we solve the transfer equation, or should we solve the moments of the transfer equation? Not clear which is the best way to go. Which frame should you write the equations? In the co-moving frame, in the lab frame, in a fully relativistic problems? Which way are you going to handle that in some kind of mixed frame? The issue is that there are radiation material interaction terms, say, for example, scattering. And in the fluid frame, scattering is isotropic, but in the lab frame, the fluid is moving, and so then the scattering is anisotropic. And the way you treat the scattering terms is different in the fluid frame versus the Eulerian frame. And so which is the best way to do it? That's a matter of research. If you are going to use the moment equations, you're going to have a closure problem. It's exactly like the issue of taking moments of the Boltzmann equation to derive the equations of hydrodynamics. They're closed by an equation of state, where the pressure of the fluid is related to its density and temperature. We don't have such a thing for radiation. The closure relation for radiation is, in general, not possible to write down sort of analytically, and so we need some kind of closure we're going to have to calculate. The mathematical nature of the equations makes them complicated as an applied math problem to solve, because they're hyperbolic in some limits, but they're mixed hyperbolic parabolic in other limits, and that makes numerical algorithms, they have to be able to transform smoothly from one frame to another, from one limit to another. That's not easy. There's a very wide range of timescales in the problem. You have fluid flow timescales setting a CFL constraint, just as you're already used to. But in addition, now we have a speed of light in the problem, and that introduces a very short timescale, the light crossing time. And you often cannot integrate the equations explicitly on a light crossing time, so you need some kind of implicit method. Moreover, there are material radiation interaction terms, there's heating and cooling terms, so there's timescales associated with the relaxation of those terms, and so that's also going to introduce new stiff terms to the equation. So you're going to need implicit or semi-implicit method. And I can go on and on. Frequency dependence adds another whole dimension. So rather than just spatial dimensions, you've got the frequency dimension to discretize. Non-LTE effects means you really need to put in calculations of level populations. It just gets harder and harder and harder. So I don't think anybody is doing numerical solutions including all of these aspects. We pick our poison at the moment and try to solve the problem with as much generality, but frequency dependence is very much a topic for the future. Non-LTE radiative transfer, still really a topic for the future. So all this complexity means that different people mean different things when they say radiation hydrodynamics. So I'm going to give you some examples. For one example is you just solve the fluid equations with a source term, which is computed from the material radiation interaction term and the transfer equation. So there's a cooling term and a heating term. due to absorption and emission of radiation from the fluid. That's basically what we covered last time as optically thin cooling. You can add in explicit terms for heating and cooling due to radiation, and some people call that radiation hydrodynamics. And that's a very simple thing to treat numerically. We saw last time you add these source terms. I wouldn't call that radiation hydrodynamics, but you see in the literature sometimes it's called radiation hydrodynamics. But that's not what we mean in this lecture. I'm not going to call that radiation hydrodynamics. In some cases, the fluid is optically thick, and so you can't add just an optically thin cooling law. You have to add in another variable, the radiation energy density, for example, and then you have to solve a diffusion equation for the radiation energy density with this material radiation interaction term in both the fluid energy equation and the radiation energy equation. The radiation and fluid can exchange energy through absorption and emission. And so now you've got to solve another dynamical equation along with these source terms. And if you're in very, very optically thick media, stellar exteriors, middles of protoplanetary disks, for example, then this is the approach you need to take. We're now adding an extra equation to solve. Sometimes the transport of energy is not the issue by photons. It's the transport of momentum that's the important issue with photons. So instead of solving an energy equation with source terms, you have to solve the momentum equation with radiation source terms. So now it's the same interaction terms, but now there's the moment includes the directional product here, the directional dot product with n, or the vector n. So we have to compute a momentum flux from the radiation field and add it to the momentum equations. And we don't have an energy equation here because often it's okay to assume that the fluid and photons are so tightly coupled they're in isothermal approximation. They stay at the same temperature. So this is used to calculate the structure of stellar winds in hot stars. So line-driven winds require solving the transfer equation to compute this force, often using the Sobolev approximation, as Paul mentioned the other day, and then including that in an isothermal system of hydrodynamics. And that is radiation hydrodynamics as well. And so what we know about radiatively driven winds from hot stars, in fact, it's a fascinating field of recent results in radiatively driven winds from hot stars. That's a problem where you're only solving a subsystem of the equations. Calculating this force can be extremely complicated. People use the Sobolev approximation, but in fact that approximation is violated in many multidimensional line-driven wind cases. And so doing the full transport problem, the full line transport in the moving medium, is an incredibly challenging problem. I don't know anybody doing that in multi-dimensions from first principles to look at line-driven winds. So I mean, I could give a whole lecture on just this one topic of how do you compute line-driven winds forces, but we're just going to move on to yet another example of radiation hydrodynamics. This is the case where both energy transport by the photons and momentum transport by the photons is important, and moreover, it's not fully optically thin everywhere, so you have to treat transport effects. And so now we have to solve the fluid equations plus a radiation energy equation, a radiation momentum equation with the appropriate source terms linking the material and radiation energy densities and the material and radiation momenta. So now we've added another couple of hyperbolic equations to the system. We've added some more moments, an energy density, a flux, and a radiation pressure tensor. We're going to have to try to evolve these equations. And you can see the closure problem now. I have more unknowns than equations. I have a gas pressure here, but I also have an equation of state. I haven't written it down, but there's an equation of state that you can use to close that. But I've introduced a radiation pressure here, and I can't write down a general equation for the radiation pressure. I'm going to need something else to close this. So this is the problem I'm going to call radiation hydrodynamics, and this is where I'm going to focus most of my time. So the methods we're going to use in each of these 4 different regimes is very different. I'm really going to focus on methods for this regime. So the basic challenge is we've got to try to solve the transfer equation. So here we've written it out in sort of generality, radiation transfer equation. You can think of this as a Boltzmann equation for the photons. And you can think of the specific intensity I as the distribution function of the photons. And so doing radiation hydrodynamics is kind of like fluid dynamics. If you're solving the transfer equation, you're doing the most fundamental description of the radiation field. You're evolving the distribution function for the photons, and then you can take its moments to get an energy density, a flux, and a pressure that you need to calculate in the fluid equations. However, just like in fluid dynamics, solving this equation is very, very challenging because it has a large dimension in phase space. It's got 3 spatial dimensions, plus time, plus frequency, plus 2 angles, because the radiation intensity is different along different angles in space. And so you have a very large dimensional problem if you're going to try to integrate the transfer equation. So people like to get rid of some of those dimensions by taking angular moments of the radiation field, just like they do in hydrodynamics. Taking angular moments makes the problem easier. And so people talk about solving the moment equations, and I'll describe a lot about trying to solve the moment equations instead of the transfer equation directly. But keep in mind that there's this choice. You could solve the transfer equation directly, or you could try solving the moment equations. In fact, that leads to your sort of choice of numerical algorithms. From the very beginning, you can choose to solve the equations using a mesh, or you could choose to solve the equations using particles. And even though we're using a grid for the MHD, we could still choose to use particles to integrate the transfer equation. And so again, each method has its advantages and disadvantages. On a grid, if you were to discretize the transfer equations or its moments on a grid, then it could be more accurate with less noise, as I'll show you in a moment. But it comes with a disadvantage that it's difficult to include scattering and line transport. It's very, very expensive. Particle approaches, kind of like Monte Carlo methods, or not like, but Monte Carlo methods, are very flexible, so they're easy to include frequency-dependent transport, scattering, non-LTE effects, very straightforward to include into a Monte Carlo type approach. They're embarrassingly parallel. You can just set off gazillion packets with some number of packets in each processor. But their major problem with them for the applications I'm going to consider is the fact that there's just particle noise. There's shot noise in the method, and that's going to couple to the hydrodynamics. And this is a serious issue. I mean, for many applications, this may not be an issue, but for the applications we're thinking about, this is going to be an issue. And this is, you can see this directly in this sort of test. What's shown here is a slice, a 2-dimensional slice from a 3D simulation of an accretion disk. So this is a small part of the atmosphere in an accretion disk. The midplane of the disk is down here somewhere. This is the upper atmosphere of a radiation-dominated accretion disk. So you can see the density field in this 2-dimensional slice from this disk simulation. And then these bottom 3 panels are the Eddington factor. So it's the measure of the geometry of the radiation field. It's the ZZ component of the radiation pressure tensor divided by the energy density. So this is a measure of the geometry of the flux and transport in the vertical direction of the radiation field. And so these 3 panels plot this component of the Eddington tensor, calculated using a full transport method, so discretizing the equations of transfer on a mesh and solving it using a method called short characteristics, I'll tell you about in a bit, using 24 different angles to discretize in different directions. Here it is with 168 angles. Very small change between the structure. So increasing the resolution is converging to the solution. But even with 24 angles, you have a very, very good description of the radiation field. And here it is with Monte Carlo using 10 million photon packets. And I apologize, the discretization of this image from the paper has introduced pixelization here. But on this side, there is a lot of noise. If you look at the boundary of the colors, there's a lot of non-pixelized noise here. So if you look at the actual image in the paper, this is what the image looks like, and these are very, very smooth. There's at least sort of 1% noise in the Monte Carlo solution. And if you have a Godunov scheme, 1% noise is huge. Those are linear waves. You're going to be launching linear waves all over the place. You're going to be launching a turbulent cascade of all these linear waves from the noise just introduced at each part. I mean, basically, if you want to get 1% error, it's a root n problem. You need a large number of photons in each cell in full 3D to beat the noise down to a very, very small value, the kind of small values you need for for grid-based schemes like Godenoff methods. And already, you know, at 10 million photons, this took 100 times longer to calculate this solution using Monte Carlo than it did using short characteristics, even with its 168 angles. So it just looks like a losing proposition to beat the noise down sufficiently for these kind of problems. And so putting in the rate of transport using Monte Carlo and the kind of applications that we're looking at doesn't look like the right way to go. It looks like meshes are going to be the better way to go, despite the flexibility and ease of using Monte Carlo. Question? I'm sorry? I'm going to get back to the FLD in just a minute. Yeah, so I'm going to return to this image and talk about the FLT in just a minute. Okay, so we're going to focus on grid-based methods now for the rest of my lecture. I'm not going to be talking about Monte Carlo methods. But let me start with a simpler problem than the full radiation hydro problem that we were talking about before, but nonetheless a very important one in astrophysics, mostly because it relates to both ionization, growth of ionization regions in the interstellar medium, so in hot star formation, and also it relates to reionization in the universe, a very important problem in cosmological structure formation. So there's a lot of interest in numerical methods for ionizing radiation transport right now. And so I thought I would say a few words about how to do that. There has emerged a very nice set of algorithms for doing this problem, and most people are following these same approaches, so I thought I would at least mention it. So for the ionization radiation transport problem, now it's very much like the first example I showed you, except it's not completely optically thin everywhere. You need to solve the hydro equations with heating and cooling terms in the energy equations, and recombination and ionization terms in an equation for the neutral fraction of the medium. So it's a two-fluid problem, neutrals and ions. You're solving two continuity equations, and there's a recombination ionization rate embedded in the neutral evolution equation. And so we need to calculate the ionization rate. So that's the sum of the ionizing flux from all sources n in the problem. So you imagine having n discrete sources of radiation at any grid point. I need to calculate the ionizing flux as a sum from all the n points ionizing, producing radiation at that point. And so that's this quantity here, where this tau, so it's just the flux diluted by the geometrical factor r squared from the distance from the source, multiplied by this e to the minus tau, the optical depth. And so the hard part's calculating this optical depth. For every grid point in the problem, you have to calculate the optical depth to every ionizing source. And actually, this is just like the shielding problem that Paul described yesterday. Another reason why I mention it, it's just like having to calculate the extinction, the AV, the column density at every grid point to infinity in order to calculate the cooling rate and heating rate from stellar radiation field in the interstellar medium. So the algorithm is exactly the same. People have adopted this adaptive ray tracing approach introduced by Abel and Wendelt and extended by Wayland and Norman. This HealPix library is used to do adaptive ray tracing on the mesh. And so this HealPix library is the fundamental method for following rays from every point source to every grid point on the grid. You need to add a little bit of bells and whistles. You need to limit the cooling rate and ionization in mixed cells, just like I discussed yesterday. And then it works extremely well. I show one test from a paper that Mark Krumholtz wrote on this algorithm introduced for studying growth of H2 regions in the interstellar medium, but it's very similar to tests of cosmological codes. This is a test of a growth of a D-type ionization front in a uniform medium. The numerical solution is overplotted the analytic radius as a function of time, and again it agrees extremely well. Here's the error in the solution, and here's a two-dimensional image, and the dashed line is the analytic radius, the expectation of the radius that it should be at that time, and again agrees extremely well. So if you're interested in reionization or H2 regions, then I would encourage you to read this literature, which describes these methods extremely well. And again, it sort of overlaps with what's needed for doing the SM problem. But let me move on from that quick example to the more general problem, the full rad hydro problem. So now let's just go back and go to the last of those four types of radiation hydro problems, the one that involves solving the Euler equations, so the Hydro equations in black, Maxwell's equations for the magnetic field, so all the blue terms, the induction equation in blue representing all the MHD terms and equations, and then finally we're going to introduce the moment equations to treat the radiation field. So the red terms are the source terms in the energy and momentum equations, and then we have the 0th and 1st moment equations of the radiation transfer equation to evolve the radiation energy density and radiation flux. So the source terms are an issue here. This is where you have to choose a frame. And in this approach, we're going to adopt the mixed frame, where the radiation variables are written on the Eulerian frame, but the interaction terms are calculated in the fluid frame. And then you do a Lorentz transformation from the fluid frame to the lab frame to transform the source terms back into the appropriate frame for the fluid and radiation variables. And you only do that to some order in V over C. So you do an order V over C expansion of the Lorentz transformation of the source terms from the fluid frame to the lab frame to calculate these source terms. And this has been done for us after sort of several papers and a couple of decades of research to get all the terms in the expansion correctly to order V over C in all frames is a non-trivial task. Again, Mark's participated in this, written a paper on this topic. And so we're using the sort of latest and greatest formulation terms that are very similar to what Mark had derived in his paper. So why do this way? Because it reduces the dimensionality of the problem. We get rid of the angular distribution of the radiation field by integrating over angles by taking moments. We just have a system of three spatial dimensions plus time, system of 4-dimensional PDEs. The problem is that PDEs are of mixed type. They're hyperbolic, parabolic, and different limits. There's this wide range of time scales. These source terms can be very stiff. Remember the cooling problem again? I mean, the cooling rate could be much, much bigger than the flux divergence. And we need a closure relation. These are all things I've already mentioned. How do we compute this? Normally, you can just write down schematically an equation of state for the radiation field is some tensor F times the energy density, where F is some unknown quantity called the Eddington tensor. So how do we compute F? All we're doing is burying all of our ignorance into this unknown tensor F. And so we need some way to calculate the Eddington tensor. Well, one way to go, and one very popular way to go, is called flux limited diffusion. And that's to introduce an ansatz that the flux should everywhere obey Fick's law of diffusion. Just write the flux as a diffusion coefficient times the gradient of the energy density. That's going to get rid of one of the moment equations. We don't need an equation for the flux anymore because we're going to adopt this ansatz. And we're going to need some diffusion constant here. But we need to obey causality. If we just allow the diffusion to be any value we want, we could have superluminal transport. We could have energy being transported faster than the speed of light. So you've got to limit this diffusion, this flux, by adopting a diffusion coefficient, which is speed of light divided by opacity coefficient times some factor lambda, a flux limiter it's called. Lambda is some arbitrary function that's used to limit the flux in the appropriate regimes. And then the MHD equations, the radiation MHD equations, are much simpler. Now we've gotten rid of the flux equation. We can just write down an energy equation for the radiation field. And that's all we need to solve, is one additional energy equation. So we have two energy equations still to solve, but we've gotten rid of the flux equation. In fact, we've gotten rid of 3 equations because in 3D there's one flux equation for each component. So that's a significant reduction from 4 equations to 1. Yes?
In the diffusion coefficient, what's the denominator? What's chi?
Chi is opacity here.
Oh, the opacity.
Yes. Okay. So,
there's a subtlety here maybe worth pointing out that chi is the total opacity, not the opacity per unit mass.
Yes.
The conventions here are different in astrophysics than they are in radiation hydrodynamics.
Right. So I may use chi and kappa interchangeably, one being per unit mass, one being not per unit mass. Okay. So the advantage of doing this is it's made the problem much easier to solve. But there are some cons, of which we don't really know, we don't really have an idea of how important these cons are until we try it out. But some of these cons are that we've lost information about the direction of the flux now. We're assuming it's always, the radiation flux is always in the direction of the gradient of the energy density. That doesn't need to be true. The flux is independent of the direction of the radiation energy density in optically thin media. So this is potentially a big assumption. We don't really know how big an impact it's going to have until we try it out. The magnitude of the flux may not be correct because, again, we're assuming it's some diffusion coefficient times the gradient here. We've dropped the radiation inertia because we've dropped the radiation flux equation. There's no dF/dt, which is responsible for inertia in the radiation field. And that means we're going to get superluminal wave speeds in very radiation-dominated fluids. I mean, what limits the speed of propagation of waves to the speed of light is relativistic effects. At some point, the radiation inertia is large enough that you can't oscillate too rapidly. You can't have frequencies that would produce superluminal transport. But since we've dropped the radiation flux equation, we're not going to stop that from happening. If we're solving very, very radiation-dominated media where the radiation energy density is much, much, much bigger than the gas pressure, then this could be an issue. And then we've lost things like the full tensorial components of the radiation pressure tensor. For example, we've lost shear viscosity, which are the off-diagonal components of the radiation pressure tensor. We don't have a pressure tensor here, so we've lost those potentially important shear components, again, in radiation-dominated fluids. Again, these are all things that we all know about, but we're not quite sure if they're important or not. What is this flux limiter? It is really an arbitrary function. You can pretty much choose what you like, whatever you like, as long as it has obeys certain limits. The most popular form was introduced back in the 80s by Livermore and Pomeranian. There it is. Lambda of R is this function, where R is the sort of normalized gradient of the radiation energy density, grad E over E. And its only purpose of this flux limiter is to give the right radiation flux in the right limits. In the optically thin limit, we want this flux limiter to reduce to 1 over R such that you get the flux being of order C times E, the speed of light times E. That is the maximum rate at which you can transport energy. You know, this is the radiation energy density. The radiation is moving at the speed of light, so the highest rate of transport is to move the radiation energy density at the speed of light, so the flux has to be CE in the optically thin limit. And this will reduce, if you use this form of the limiter in the optically thin limit, you will recover this limit correctly. Similarly, in the optically thin limit, you want this flux limiter to reduce to the diffusion approximation. That is, you want it to be 1/3. And again, this limiter, if you just work out the limits of R equals 0 and R equals infinity, it has the right limits. In between, it's doing some functional form, and you can choose many other different functional forms. There's forms due to Minerbo and many other authors, and as long as they have the right limits, they're all acceptable as flux limiters. And you put this into your code and you integrate it, and it passes many tests very well. So for example, here is the structure of a radiation modified shock wave. Here's the temperature and the flux in the shock wave. So in the post-shock medium, the gas is hot, it's radiating, photons are traveling upstream, they're preheating the gas, so there's a slight increase in temperature ahead of the shock wave. Of course, energy is conserved, so the gas is cooling a little bit due to the emission of photons which are propagating upstream, and you can see the flux has this characteristic peak shaped around the interface. The solid line is an estimate of what the solution should look like by Zeldovich and Razor, and the dashes and squares are the solution from 2 different limiters. This Livermore Pomeranian and another one I mentioned due to Minerbo. And you see that for the temperature, it makes very, very little difference what limiter you use. For the flux, it does make a more substantial difference between which limiter you're using. But overall, this seems to be a pretty good qualitative agreement with what you would expect for this solution. So that looks pretty good. Now, I've skipped over some important aspects of the numerics here. Along the way, we've had to do implicit differencing. We've had to difference those moment equations. Even with flux limited diffusion, we have to solve the radiation energy equation implicitly. And that's going to lead to large sparse banded matrices because the radiation energy equation has spatial operators in it, so you're coupling neighboring grid points in a complicated way. And so you're going to get, in 2 dimensions, not just a tridiagonal, but diagonal plus off-diagonal bands that you're going to have to solve implicitly. So you have to invert this matrix every time step. It's a nonlinear system, actually, and so you're going to have to use Newton-Raphson iteration to converge this nonlinear system every time step. You're going to need many, many solutions of this matrix every time step. Typically, people use things like GMRes or ICCG or multigrid to invert this matrix every time step. In 3D, it just gets even worse. That 2D matrix is replicated n times across the diagonal with 2 more off-diagonal bands introduced in 3D. So now the matrix is getting very, very large. And so generally, the most expensive step in the entire MHD algorithm is now inverting this matrix. And so the entire radiation hydro problem comes down to doing this linear algebra problem efficiently every time step to integrate the equations. So that's led to some recent interest in using what are called reduced speed of light methods. I won't really say much about them except to introduce the concept. The idea is, well, to heck with the speed of light. Whoever said the speed of light had to be this fancy number, this big number? Let's just make it whatever we want. Let's just make it, say, 10 times the sound speed or 100 times the sound speed. As long as it's a big number times the sound speed, it's okay. I mean, why does it have to be 1,000,000 times the sound speed? Why can't it just be 100 times the sound speed? Won't the dynamics be roughly the same? Well, in many respects, yes. A lot of the things will be the same. Unfortunately, some of the things won't be the same. So you have to be a little bit careful. So by doing this, by making the sound speed the speed of light much smaller than it should be, you can use fully explicit methods and just integrate things in the light crossing time. If you make the light speed 10 times the sound speed, you'll need 10 times more time steps, but that's okay. That's still a lot cheaper than solving the full implicit system. So it's kind of like a sub-stepping method where you're going to use 10 time steps to obey the C-alpha condition on the speed of light to evolve one sound crossing time with a 10 times smaller sound speed than speed of light. But it does affect the dynamics, and so care is required. And there's a nice description of this algorithm in a recent paper, along with a nice description of the limits of this method. So it's an intriguing idea, and its use is now being explored. Whether this is going to work well or not in all regimes is now sort of being explored certainly by Eve Ostreicher, her students, and postdocs and other groups as well. So that's one way to get rid of the implicit issue in the equations. But there's still this flux limiter in here. Let me return to this picture here. This is, again, the two-dimensional slice of a 3D radiation hydro simulation of an accretion disk. This is the density field. This is the ZZ component of the Eddington tensor computed with short characteristic Monte Carlo. Same picture I showed you before. But now let's focus on this panel here. This is the Eddington tensor that flux limited diffusion would predict for this density field and this temperature and radiation energy field. And you notice that it's very, very different than either short characteristic Monte Carlo. They're consistent with each other. They all agree with the same radiation field. But the flux limited diffusion, it's neither the same pattern nor is it the same values. Notice the scales are very, very different here. This is 1 and this is 0.4. The flux limiter differs by a factor of a few, not only in amplitude but also in its distribution. So here's a concern. The flux limiter that radiation, or the ZZ component of the radiation pressure tensor predicted by flux limited diffusion is order unity different than what you would have got from solving the transfer equation and calculating that pressure tensor directly. So yes?
So I've never seen this plot on the same color scale for both. And it seems to be plausible that what's going on is that basically both short characteristics and FLD are giving you that it's a third sort of in the high density region.
Uh-huh.
Right, I mean, so maybe it's 0.32 versus 0.35 or something, right? But that's a very small difference. And the order unity difference is only sort of above in the low density atmosphere.
Absolutely. The difference is all in the low density region in the atmosphere. But that's what's most worrisome, because in the optically thick part, everything's a third. We all agree with that. But the cooling rate from the disk is determined by where the photosphere is, where it's no longer optically thick anymore. And so the entire dynamics is controlled by the optically thin part, which is where the radiation flux determines the cooling rate. And so precisely where you care about it the most is where flux limited diffusion is doing the worst. In the optically thick part, where it's diffusion anyways, then everybody agrees on that. That's fine. No doubt FLD works for diffusion. So even so, well, gosh, it's hard to know what this is really going to do to the overall dynamics of the flow. So we still have to sort of try to compare. But there is a concern that flux limiter diffusion is maybe not the right approach here. So there's now a lot of interest in trying to do better. There's a new moment. It's actually not that new. It's been around for quite a while, but astrophysicists are really jumping on it lately and using it a lot, called the M1 closure. It reintroduces the radiation flux equation and uses a tensorial form for the Eddington factor, but still it's computed using only local quantities. So you calculate an Eddington tensor with multidimensional components, but you use only local information, the radiation energy density and local values of the radiation flux, to calculate what that tensor should be. Again, I'm not going to go through the details and write it out. You can see this paper for the formulation of the method. It keeps flux as a separate variable, but again, it uses only local information. The problem with M1 is that it fixes one problem, and I haven't shown you this example, but another problem with flux limiter diffusion is because there's no information about the direction of the flux. You can't have shadows with flux limiter diffusion. This is, again, a well-known issue. Again, not clear that what that really has its impact on real flows, but this shadowing has been identified as an issue, that when you have flux limiter diffusion, you cannot cast shadows in the radiation field. With M1, you can now cast shadows. So it fixes that problem, and you get shadowing properly. But instead, you introduce some other new problem, which in many circumstances is much worse than the lack of shadows in flux limiter diffusion. Namely, with M1, photons interact. They collide. If you have two beams of radiation, with M1, they will merge and collide and then go straight up again. That's not what's supposed to happen with photons. They're supposed to propagate through each other. They're not supposed to interact with each other. You can see this is in a test example here. It's two spheres radiating two hot spheres. Here's a formal solution to the transfer equation. This is the solution at some time, intermediate time, where the radiation front is propagating away from these two spheres. With M1, you see that the photons have collided on axis, have merged, and now they're squirting out along the top axis. So there's a huge flux in the vertical direction here. It's kind of like two stars producing hot star winds. The stars are colliding in a shock front and squirting out the top and bottom. This is what happens with M1. So if M1, if you have multiple sources of radiation, you're going to have interaction of the photons everywhere. It's not clear what that's going to do. I mean, maybe it's okay, but you just don't know. FLD actually looks to be much better on this problem, in my opinion, although there's too much energy density in the middle here compared to the formal solution. There's a little bridge here, shouldn't be there, but maybe that's kind of a sort of minor thing. So how are we going to do better? Let's just jump straight to the quick. What we need is a better way to calculate this closure relation, this Eddington tensor. We're going to use something called we're going to use short characteristics to compute a formal solution of the transfer equation and calculate this Eddington tensor from first principles. That seems to me the most fundamental and the best way to go. The source terms I mentioned are very stiff. That's an issue, but we can get around using modified Godin methods. I'll mention that. And we still have to be implicit on these range of timescales, I think. I mean, I'm going to stick to the approach where we're going to use an implicit formulation of the equation rather than a reduced speed of light. Let me just focus on this variable Eddington tensor. So one attractive way to go, which has been, again, around for decades. This is not something that we've invented. It's been used for stellar atmospheres. It's been used for radiation hydrodynamics for many decades. The idea goes back to the 70s and how to do this approach. What you do is you solve the transfer equation on a mesh using the time-independent form of the transfer equation. This is appropriate for problems where the light crossing time is extremely short compared to the dynamical time of the flow. So as the flow is evolving, the radiation intensity can come to equilibrium essentially instantaneously with whatever the instantaneous flow pattern is. So we're making the approximation that the specific intensity is coming to some kind of steady state instantaneously with however the flow is evolving. That's a good approximation if you are in the regime where the light crossing time is short compared to the flow evolution timescales. In that case, we solve the time-independent transfer equation using a technique where we're going to use rays to discretize the angular distribution of the radiation intensity I. But rather than using something like heel picks or what's called long characteristics, where we have to use a ray from every grid cell to every other grid cell in the problem, that will be extremely expensive. For every grid cell, we would need n rays, so that's an n squared method for the entire mesh. Instead, we're going to just use ray segments that end at the cell boundaries. And where we need to know the starting intensity to integrate the specific intensity along this ray segment, we're going to interpolate from the previous solution at neighboring grid cells. So we know the specific intensity from the neighboring grid cells. We'll interpolate to here, calculate it to there. That'll give us a specific intensity on this face that we can use to then interpolate on the ray segments for the next cell and so on. So this technique of breaking up the intensity into discrete ray segments in each cell and using interpolation to initialize and propagate the radiation across the entire mesh is called short characteristics. Once we solve the transfer equation using short characteristics, we now have the specific intensity on the entire mesh over all angles, over all rays that we've chosen. We have complete freedom to choose whatever rays we want, whatever directions we want to discretize the angular distribution of the radiation field. When we have that information, we just do these formal moments. We just integrate the specific intensity over angle to calculate the radiation energy density and then to calculate the radiation pressure. We just take the second moment of the specific intensity numerically. We just do a quadrature. And that gives us the ratio of P over E, which is the Eddington tensor that we need. And then we use that Eddington tensor in the dynamical equations, integrate the equations for one time step, stop, redo the solution of the transfer equation, recompute the Eddington tensor, integrate the equations for one time step with that new value of the Eddington tensor, stop, do it all over again. So we're replacing some local description for the Eddington tensor with the formal solution of the transfer equation to compute it directly. And that's the approach here. And this method of short characteristics works well. It's as I mentioned, it's been developed in the late 70s, sort of perfected, if you like, in the 80s. Hasn't really progressed much since Kuznets-Auer's techniques. I've already mentioned long characteristics as the alternative approach, and in the interest of time, I'll just skip on to demonstrating this actually works. You know, you can take this formal solution and you can test it with various problems. You can take the so-called flashlight beam test. So here's a two-dimensional domain. At the bottom, you introduce a beam of radiation, a flashlight. It's got periodic boundary conditions, so the flashlight beam leaves this side, comes back in this side, goes there, just wraps around till it leaves the top of the mesh. And to demonstrate that it doesn't have photon interaction like in M1, you can have another flashlight beam that goes the other way, and you notice that the beams cross quite happily with no interactions. It can produce shadows. Here's a dense region of high opacity in which you're shining two light beams on, and behind it you get the appropriate shadow structure with umbra and penumbra, just like you would expect. So it all works. Yes, question?
So the light beams here are just a single ray? Or?
Intensity along a single direction, yes. So you initialize the specific intensity with 0 at all angles except for one angle, and one angle has a non-zero intensity. That's right. So because of the spatial interpolation required in short characteristics, there is diffusion of the beam. So it doesn't stay just in one exact direction along a very narrow slice. There is some spatial diffusion from the interpolation algorithm. That's why there's a slight spreading of the beam. But remember, this is only going to be used to do angular quadratures to calculate an Eddington tensor. So I really don't think that the spatial diffusion here is a problem. In fact, it's actually having too little diffusion is a problem. But I can get into that later if you're interested. So that's how we're going to calculate the Eddington tensor. We still have these stiff source terms on the right-hand side. We're going to use semi-implicit update. I'm going to kind of skip over exactly how all that works, but it's kind of like the source terms we discussed yesterday. So we're using something called a modified Godnoff method to incorporate those source terms stably into the Godnoff scheme. And then finally, we are still forced to use this implicit solution of the radiation moment equations. However, one big advantage of this formulation is that these equations are linear in the unknowns. They're linear in the radiation energy density and flux, which are the two unknowns we're trying to invert for, and therefore we don't have to use Newton-Raphson iteration to converge the linear system. One linear solution per time step's all that's required in this particular system. So we're going to use backward Euler differencing because it's the most stable, although not as accurate higher methods as a first step. We're just going to do the simplest thing possible, backward Euler. So along the way, we've developed this algorithm. Mostly a student at Princeton, Yanfei Zhang, and a postdoc at Toronto, Shane Davis, have participated in this. We've some lessons learned along the way to think about if you maybe develop complicated codes. One thing we learned is that while the conservation form of the equations is highly preferred, and you may read lots about why it's absolutely essential, the bottom line is that, in fact, conserving total energy in radiation hydrodynamics is very difficult because you have these large linear systems that you're converging to some error tolerance, and unless you construct a system such that the error is conservative, you're going to break energy conservation in the implicit solve. And so it's not really clear that a completely strong conservative form really is an advantage in radiation hydrodynamics. We also learned that writing our own multigrid solver was much better than using a canned library like HiPACC or PETSI. That is counterintuitive because these libraries have, hundreds of person years of effort of code development and optimization to get the most efficient linear solvers possible on parallel architectures. So how is it that, a bunch of yahoos can, astrophysicists can figure out how to write a better library than these computer scientists? That's not what I'm saying. What happens is that our matrix has a very particular sparsity pattern. There is no function in these libraries that's been optimized for our sparsity pattern. Our matrix is very specific to the equations we're solving. So we have to use a general form of the linear solvers in these libraries. Those general forms must work for all kinds of matrices. Therefore, all sorts of optimizations that are possible can't be used because they have to be completely general. So we can write a special purpose solver optimized for our matrix, which works better than the general purpose solvers that are in these libraries. That was a shocking realization to us. And so again, unless you can use the highly optimized versions in these libraries, it's probably better to write your own. Okay, so let me just continue with some tests of the method. I mean, one nice test I always like is convergence problems, because then you can measure whether your scheme is converging and whether there are bugs. If it's not converging, you see them right away. So a good test is linear waves. It's a quantitative measure of the error in the scheme and the convergence rate. But this is where the physics of radiation hydrodynamics again becomes kind of interesting and a problem. There are many wave modes in radiation hydrodynamics, depending on which regime you're in, whether you're in the optically thin or thick regime and whether you're in the radiation pressure dominated or not regime. And so there's actually a large phase space that you have to solve here. And I'm only going to show you one particular case involving a particular range of opacities and radiation pressures. So here's the case where the radiation pressure is small. P is the ratio of P rad to P gas, basically. So if it ranges from small radiation pressure to large radiation pressure, and this sigma A is the optical depth per wavelength in the solution. So from small optical depth per wavelength to large optical depth per wavelength. And the solid dashed and dotted lines are the analytic solutions for the dispersion relation in these regimes. And then the stars are the numerically measured phase velocity and damping rate from the solution. And again, very nice agreement. Again, you can measure the error at any single point and plot its convergence rate with resolution. And you reproduce that in the radiation-dominated regime. The method is only first order. That's because we're using backward Euler implicit differencing, which is only first order, as you know. But in the gas pressure dominated regime, the method is second order accurate. That's where the implicit solve, the truncation error associated with the implicit solve is not dominating the overall truncation error. And so we're seeing second order convergence in that regime.
Jim, what's going on? Sorry, can you go back? What's going on at sigma A of 100 point? Looks like the three stars are.
Yes. So, I mean, they're not right on the points. You mean here?
Yeah, well, it looks like they're all on the black rock line rather than two of them following the red and blue lines.
Right. So this here we only ran. So it's a matter of convergence here. So we ran a low resolution version of this because it's so expensive. And it's a fully 3D test with the wave at some angle to the grid. And so the error associated with these modes is actually quite large still for these linear modes. And what we should have done is done a much higher resolution and would have converged to the lines. So the particular data we used here, the error was still very substantial. So we're up here somewhere in this exactly. It's the resolution. Now, I do have to admit that the scheme, it's only first order conversion in these regimes at high radiation pressure, and so you need a lot of resolution to beat the error down to a very small value there, if you really want to do that. So not a fundamental problem with the method, but rather a challenge to getting accurate solutions in that regime. And another good test is radiation shocks. I'm kind of running out of time here, but let me go through these radiation shocks because they're an interesting demonstration of the physics of rad hydro. Here, it's like the solution I showed you before. You have a supersonic inflow. It's going to shock and then have a post-shock outflow. But in the post-shock temperature, it can be high enough that it produces photons that propagate upstream and preheat the gas. So you get a precursor. And then behind the shock front, the temperature has to drop to conserve energy to produce the flux that propagates upstream. So there's a relaxation region. And depending on the conditions in the flow, the Mach number, you can either have a discontinuous jump in the temperature, or you can just have a smooth, continuous profile. It all depends on how much radiation flux is moving upstream, and that depends on the Mach number. When the post-shock, when the pre-shock temperature here is below the post-shock temperature here, we call that a subcritical shock. And so we're going to look at, there's sort of a large nomenclature in the structure of these shocks depending on the Mach number. And so it's useful to go through a wide range of Mach numbers for the same test problem and see whether or not you can produce the appropriate shock structure in each regime. You see, this is demonstrating why radiation hydro is so much more difficult. In MHD, a Riemann problem is a Riemann problem. There's only one solution to it. The shock structure doesn't change its form dramatically. There's just a shock. There's just a discontinuity. There's no shock structure in hydrodynamics. In radiation hydrodynamics, there is structure to the shock, and it changes depending on the Mach number. So at very low Mach numbers, you have a very smooth profile. At higher Mach numbers, you get a discontinuous jump. As you increase the Mach number, you begin to get a little peak, a relaxation region behind. You get a so-called Zeldovich spike. As you increase the Mach number even higher, the pre-shock temperature becomes the same as the post-shock temperature, and this jump goes away, although there's still a very, very tiny spike there. So these blue lines come from a semi-analytic solution to the equation. So we actually know what the right answer is supposed to be. And the dots come from the numerical solution. And it's very reassuring that the numerical solution captures not only the smooth behavior in those regimes, but also these discontinuous jumps in other regimes. So that's very, very reassuring. You can also do this problem. So that shock structure was using the Eddington approximation, where the Eddington tensor is just a third. That's because there's it's actually, the problem is the semi-analytic solution itself is too difficult if you don't make that approximation. The code could run the problem, but to solve the problem semi-analytically so we know what the answer is to compare to, that's too difficult to do without the Eddington approximation. But we can go ahead and run the code anyway, even though we don't have a semi-analytic solution to compare to. We can just go ahead and run the code anyway with a full Eddington tensor approach. We're not going to adopt f equals a third. And then this is the shock structure you get by running a flow into a wall. The shock propagates away. You see, here's the Eddington XX component of the Eddington tensor. It's not just a third. It's a third in the post-shock flow, but it actually drops to be less than a third at the shock front, and then increases towards 1 in the optically thin upstream flow. As you might expect, although this also demonstrates another interesting fact, is that FLD is constructed to have the right limits a third and 1. But in fact, in real multidimensional flows, the Eddington tensor can be less than a third in some circumstances. If you have a two-dimensional plane with very strong radiation propagating upstream, then that reduces the Eddington tensor to less than a third, a feature you could never get in FLD because it doesn't allow the Eddington tensor to be less than a third in any limit. And although we don't have any analytic solution, we can go back to the Zeldovich and Razor paper, which predicted what the structure of the shock should be inside this radiation precursor zone. And so these red lines are the predictions for the temperature, pressure, and flux as a function of compression ratio or inverse compression ratio. So that's upstream density divided by density. So where the compression ratio is changing is inside the shock. That's where you're going from the upstream density to the downstream density. So this is actually plotting what the inside of the shock looks like. And so these red lines were analytic predictions for what the inside of the shock should look like. The dots are from the numerical solution. And again, we get very good agreement with the analytic predictions. There was an earlier paper that used an artificial viscosity code which got very different results. And again, I think that's the difference between using a Godunov scheme to calculate shock structure versus using artificial viscosity. You've introduced a viscous term to do shock capturing. And it's not clear that that viscous term is going to do the right thing inside the shock. And this seems to demonstrate that it's not doing the right thing inside the shock. So it seems like using Godunov schemes for radiation hydro is a important step forward, or important to do.
Not a radiation pressure dominant shock. So the viscosity is doing the momentum transfer rather than the radiation.
It is a radiation, well, the radiation momentum is not dominating, but energy transport by the radiation field is dominating. You're right, that's right. Radiation viscosity, you're right, is not more important than the artificial viscosity. Right, but so momentum transport by the radiation field is not that important, but it's all energy transport in this case, in this limit, right? I think the analytic limit only applies to this regime.
Okay. Yeah, well, the case of the radiation pressure totally dominates. You should be able to do, I mean, that should actually just reduce back to.
That's correct.
A very simple problem.
Right. Moduli some optical depth effects, of course, right? So if it were completely optically thick everywhere, then that's a trivial problem. But when it's partially optically thin, that's where it gets difficult. So we're now using these techniques for applications. Raleigh Taylor instability is one of them. You're doing this as part of the test suite or the tutorial. I mean, let me just jump to the last slide I'll show you is movies. Always good to end on a movie. So here's the Raleigh Taylor instability and just hydrodynamics, a problem that you have sort of been running already in the tutorial. This is with multimode perturbation, so you're adding in random noise at the interface, and then you're evolving a heavy fluid sitting on top of a light fluid, and so there are bubbles of light fluid rising and fingers of heavy fluid falling down, and that generates turbulent mixing at the interface here, and you see all these cage rolls associated with the mixing. And here's what happens when you do this with radiation hydrodynamics in two different limits. One is the Eddington approximation, where you just assume that the Eddington factor is a third, and this is where you're doing a full solution to the transfer equation to compute the variable Eddington tensor. And the first thing you notice is that the growth rate is much less. It sits for a long time not doing anything. That's because the linear growth rate of the modes is reduced. And the second thing you notice is it's a lot smoother at the interfaces. And that's because the radiation energy density here is acting like a viscosity, as sort of Mark was suggesting earlier here in his question, that with very high radiation energy density, you are damping short wavelength modes because radiation pressure provides a viscous transport. So you get less structure in the hydrodynamics case. And what's sort of worrisome is that the VET case is different than the Eddington approximation as well. And so it suggests that the details of how you do the wave transfer at the end of the day matter. And that doing it with VET gives you a different solution, so in the VET case, the short wavelength modes are even more strongly suppressed because now you have off-diagonal components of the energy tensor as well. So it does suggest that for some applications, you're going to have to go to the full general solution, and this is just one of them. So I'll conclude. I want to emphasize again that these are not the final answer to these algorithms. This is still very much an active area of research, and methods are still being developed, and something better probably will come along. I think people are working hard to develop better and better methods. In my opinion, and this is my opinion, I would recommend that students starting today plan on solving the transport equation directly. It's not computationally prohibitive, and it seems to make a difference in some cases. So I would not recommend using FLD or M1 because I think in the future solving the transport equation is going to be the way to go. So why not start on doing that now? Finally, the real future involves introducing time-dependent transport. Remember, the method I introduced made the assumption that the light crossing time was very short, so we could solve the time-independent transport equation. For many applications, for example, accretion onto black holes, the flow is already relativistic. And so that approximation cannot be used. The light crossing time is really not much shorter than the flow time because everything's moving at close to the speed of light around a black hole. And so the future is time-dependent transport methods for relativistic problems. And it turns out that that's a much simpler problem because you can go back to explicit differencing. And so we already have an algorithm that does the time-dependent transport. And we're now extending it to full GR so we can do the full relativistic transport problem for accretion onto black holes using an ab initio solution to the transport equation and not using FLD or M1. And then again, in the future, I think frequency-dependent transport is another whole dimension that's going to require a lot of work to incorporate scattering, frequency-dependent capacities, complicated frequency-dependent effects, like non-LTE effects, and so on. So there's a lot of work to be done in the future, and yet incorporating better physics. All right, so that's I'll end here, and if there's any questions, otherwise let's do a 5-minute break again, I guess. Okay.